So, the response of the non-ideal integrator was, and if you use this in a feedback loop, this is the integrator. With a feedback fraction of 1 over k, the closed loop response turns out to be this is correct, and this has a natural frequency which is equal to the bandwidth, geometric mean of the bandwidth without the second pole and the second pole, right? And the quality factor, I should use omega p here, and the quality factor is the ratio of the bandwidth without the second pole to the second pole and the square root of that, okay? Or alternatively, the damping factor is 1 over 2 qp, right? Okay. So, when do you get critically damped response in the time domain? It happens when the quality factor Q is half or the damping factor zeta is 1. Okay. So, that will be okay. What is omega u by k? If you recall, that's the unity loop gain frequency without the second pole. Now, if the pole is 4 times beyond the unity loop gain frequency, then you get critical damping. Okay. So, critically damped response means that if you apply a step to the input, at the output you get a step response which doesn't overshoot beyond the steady state value. But it's the fastest response you get without overshooting. Of course, you can slow it down further, but it's the fastest you get without overshooting. Okay. And what is the condition for no peaking in the frequency response? What is the condition on the damping factor or the quality factor? Yeah, the quality factor is 1 over root 2, which equivalently means the damping factor is also 1 over square root of 2. So, this gives P2 being 2 times omega u by k. What will be the time domain response in this case? It will overshoot a little bit and come back. Okay. So, you can see that the second pole has moved to a lower frequency. So, if you have it at 4 times omega u by k, it gives you critically damped response. In this case, it has moved to a lower frequency. In this case, you get a response with no peaking. And this is also the largest bandwidth that you are going to get. Okay. So, we will see that soon. And what's the bandwidth if P2 is very large? So, okay, what is the bandwidth in this case? So, if this condition is satisfied, what is the 3 dB bandwidth of the system? That is, when the quality factor or the damping factor is 1 over square root of 2, what's the 3 dB bandwidth? Yeah, so it's actually, when you have a certain natural frequency and a quality factor of 1 over square root of 2, the bandwidth will be the natural frequency itself, right? Are you familiar with Butterworth filter response? So, but this is the Butterworth filter response. Even if you don't know it, it's if you can you can figure it out by adjusting it for maximally flat response. That is a response without peaking. Okay. So if the quality factor is 1 over square root of 2, you will get the natural frequency to be the bandwidth. There is no mystery here. The denominator is of this form. Okay, omega p is the natural frequency, qp is the quality factor, plus s square by omega p square. So this is a certain transfer function. If I evaluate the steady state response, I get 1 minus this whole square plus I will take the magnitude squared of this, okay, plus the imaginary part square, which is omega square by qp square omega p square. So if you look at this, we get in expanding the square we get okay, and here we get a certain coefficient for omega p square. This is the denominator, and this cancels with this if qp is 1 over square root of 2, right? So what happens then? We have simply 1 plus omega to the 4 divided by omega p to the 4 in the denominator. And what is the 3 dB bandwidth? When the denominator reaches 2, right? This is the magnitude squared. When the magnitude reaches 1 over square root of 2, or when the magnitude squared reaches 1 over 2. So when does it reach half? When omega equals omega p. Okay? So in general, I mean, this is some extra information, but the magnitude response of an nth order Butterworth filter will be of this form. Okay. So here we are talking about a second order response, so we get to the power 4, but in general, if you have an nth order response and you want to make it Butterworth, that is, you want to have no peaking at all, then you will get this has to be the magnitude response. So all the coefficients of the denominator have to be adjusted so that all the other terms cancel out. You have only one and the highest power remaining. Okay. This is the Butterworth or the maximally flat magnitude response. Okay. So in this case, if you see, then we know that q is 1 over square root of 2. So simply this is the bandwidth, right? Omega p is omega u divided by k times p2, which is 2 times omega u by k. So that is square root 2 times omega u divided by k. If you didn't have a second pole, the bandwidth would have been omega u by k. So in this case, you get square root 2 times omega u by k. So, I mean, this P2, it's a non-ideality, but by adjusting its value, it's possible to get a larger bandwidth compared to what you had without P2, okay? Because this is the bandwidth without P2, right? So, by adjusting the value of P2, you got about 40% more bandwidth, and if you call it a sacrifice that you have to make, is that you have to tolerate a certain amount of ringing in the time domain response, in the step response. Is this okay? So if you are really hard pressed for bandwidth, maybe you will not adjust P2 to be of a very high value. You will adjust it to this particular value, which gives you a large bandwidth. Okay. So if you look at very high speed op amps, this is what the condition will be. Okay. I mean, if you look at very high speed commercial op amps, if you apply the lowest possible feedback factor around it, it will be adjusted so that you get a large bandwidth. That is a quality factor of about 1 over square root of 2. Is it okay? So what happens in general as you keep reducing the values of value of P2? Let's first evaluate the poles. Okay. So where are the poles? Where are the poles of the system? Maybe you should write it like okay. So this whole thing divided by 2, right? So let's say when P2 is at infinity, where is the pole? Huh? Is this correct? Is there something wrong with this? Yeah. When P2 is at infinity, where are the poles? Omega u by k. There is only one pole. The other pole is at infinity. Okay. Minus omega u by k. That's where the pole is. This is the S plane. Okay. And as you change P2, what happens to the poles? Where are the poles when it's critically damped? On the real axis, but yeah, both poles are identical and on the real axis. What is the value of the poles? When it's critically damped, there are two poles which are on top of each other. What's the value of the pole? It's square root of P2 times omega u by k. So it is 2 times omega u by k. Okay. So as you reduce the value of P2 from infinity, this is what I am plotting here is the closed loop pole. Okay. The open loop pole is moving from infinity. When the open loop pole is at infinity, the closed loop pole, there is only one pole at minus omega u by k. So, and as the closed loop pole moves in from infinity, the other pole also starts moving in. Okay. So it moves in like this, and this pole starts moving out. Okay. And so this happens, there are two identical poles when P2 is 4 times omega u by k. What happens after that? It will become complex. So how does it become, does it go, so it can become complex, meaning one pole will go this way and the other pole will go this way. Does it go like this? Does it go in a straight line? Does it go this way? Straight line. Goes towards the imaginary axis. So in this case, it doesn't go in a straight line. Okay. So you can see that if you look at the real and imaginary parts, they describe the circle. They describe a circle. Okay. So this is what happens. I think the circle comes back to the origin or something. Anyway, the point is it goes in a circle like this. And when the two poles are at, sorry, not from here. When the two poles are at 45-degree angle from the real axis, that's when you have the Butterworth response. Okay. This corresponds to a quality factor of 1 over square root of 2, and this corresponds to a quality factor of half. So this is critical damping, and this gives you maximally flat response. Now, as you further reduce the value of P2, the roots move closer to the j omega axis. So you get a lot more ringing, and also the magnitude of the poles reduces. So that means that the response also slows down. Okay. So at least when you are making an amplifier, you will not be making the value of Q more than 1 over square root of 2, not significantly more than that. So this gives you a parameter, that is, if you want to have a certain omega u by k, which is the closed loop bandwidth you start off with, then you have to place your high frequency poles beyond a certain frequency. That depends on whether you want critically damped response or maximally flat magnitude response. Okay. Explain which one? The poles? Yeah. So what I want to do is to plot the poles of the closed loop response as I change the value of P2. Okay. So I start off with P2 equals infinity, then the closed loop poles are at, one is at infinity and the other one is at minus omega u by k. Okay. Then I look at the critically damped condition. Then the closed loop poles are at, so two identical poles at 2 omega u by k. And also when P2 is at 2 times omega u by k, you have this 45-degree angle, right? So you will have the poles will be at these frequencies. Okay, there will be of course complex conjugate pairs, and the real part will equal the imaginary part. That's why you get 45 degrees. Okay, so you start with one of the poles at minus omega u by k, and then it moves out, the other one moves in, and you will end up with two poles at minus 2 omega u by k. And if you look at the real and imaginary parts here, it describes a circle of radius omega u by k. Okay, I think. Okay. So at this point, I mean only one pole here. So this happens when P2 is 4 times omega u by k, and this happens when P2 is 2 times omega u by k. Is it okay? So as I mentioned earlier, this gives you, what's that? Elliptical. Why? X square. It's not circle. Why do you say that?
Because you have put that x is minus p2 by 2.
Okay.
Y square is p2 square by 4 minus something.
Yeah.
So y square is some x square, x minus something whole square.
So minus p2 by 2 plus minus. No, this is not plotted with versus P2, right? Okay, so what does this give you? Yeah, so the P2 is the parameter. You are plotting it. You are plotting the real part. You are plotting this. I mean, yeah, this versus this. Okay. X minus omega u by k. So this is the imaginary part. Omega u square by k square. So isn't this a circle that's offset by omega u by k? Huh? Oh, sorry, it's minus y square. Okay, okay. Yeah, that's correct. Yeah. No, yeah, I understand. Yeah. I mean, yeah, this should be plus for a circle. Okay. Okay, probably it's not a circle. I'll think about it. But regardless of the shapes, it does pass through this point. I'll think a little more about it. Okay. 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 So again, if you, and then you can also examine the magnitude response as well as the time domain response. So if you look at the magnitude response, actually one thing we can also try and figure out is what happens when P2 is very large, but we don't neglect it. Okay. Where will the poles be? Huh? 0. No. No, poles again of the closed loop response. Okay. Both are real, that's correct. But what will be the values of the poles? So actually it's easiest to also see this from the say the loop gain plot of this will be, what is the loop gain of this? It's omega u by ks 1 by 1 plus s by P2. Okay. So this is omega u by k, and I am talking about a case where P2 is far away from that. Okay. So perhaps P2 is here. Okay. So this is the loop gain or magnitude of L. Now, what is the closed loop gain? It's the feedback, the reciprocal of the feedback fraction 1 over 1 plus 1 by L. Okay. Let's ignore this part for now. What is 1 over 1 plus 1 over L? How can I plot it on this graph? So how can I plot, can I look at this magnitude of L and plot this quantity? What's that? No, let's forget 1 over h, just this. So this, sometime back I talked about the approximation that when loop gain is very large, this is approximately 1, right? So the plot will be here. Now instead of very large, we will simply say that when it's more than 1, as far as plotting the Bode plot is concerned. When the loop gain is very small, what is it? This is approximately L itself, right? This is essentially L by 1 plus L. When loop gain is very small, I neglect this. So in that case, I will follow L. Okay. Now, how do I plot 1 over h times this? I just shift it up by 20 log 1 over h. The pole values don't change. Okay. So you can do this approximation using the equation for the poles, or you can just do it from the plot. So where are the poles now of the closed loop response? So one of the poles is nearly at P2, other one is at omega u by k, and this is the result you will get when you approximate it as well. Okay. So under this condition, okay, so you get the response that you would have got without P2, but you get an additional pole at P2. Okay, this is when P2 is at very high frequencies. Now as it comes closer and closer, you can't make this approximation anymore. Okay, so you get different results. And this is a very simple approximation also. The denominator is now when the roots of a quadratic equation are real and are very well separated from each other, you can neglect either this one compared to these two, or you can neglect this compared to these two. Okay. When the magnitude of S is very large, you can take the higher two terms. When the magnitude of S is very small, you can take the lower two terms. So if you take the lower two terms, what do you get? S equals minus omega u by k. And when you take the upper two terms, you get S equals minus P2. That is, this equal to 0. This is what you want to solve, right? So in this equation, I will neglect either the lowermost term or the highermost term and then solve it. So one thing you can do is, if you suspect this to be the case, you solve it and then see that when you neglect the higher term, you get something. So that should come out to be much lower than this. Okay. If that is not true, then your approximation was bad to begin with. Okay. So in the first assignment, there is a problem where I ask you to evaluate the roots. If you do it exactly, you will get a very messy expression from which you can't really figure out anything. So this is what I intend there. Okay. Is it okay? So P2 adds an additional pole to the closed loop response, and the additional pole will be at P2 as long as P2 itself is at a very high frequency. Now as P2 moves to lower and lower frequencies, they modify a little bit, and then it also the poles become complex conjugate. Okay, and you get the maximally flat magnitude response when P2 is at twice omega u by k, and below that you even get peaking. Okay. And similarly in the time domain, as you keep reducing the value of P2, if you go below 4 times omega u by k, you will start getting ringing. So this you can think of as, if you have some, as the condition, if you have a certain parasitic pole, you can think of it as a condition on the unity loop gain frequency. Okay. So, the unity loop gain frequency has to be a certain factor below the parasitic pole, or when you are designing, you want to design for a certain unity loop gain frequency because you want a certain closed loop performance. So, this is the condition on the parasitic pole. Now, when a given technology, there is a limit on how high frequency you can make a parasitic pole. So, you will not be able to design for greater than a certain unity gain frequency. So, that's the technological limit. So, maybe in 0.18 micron technology, you will only be able to design op amps with maybe 1 gigahertz bandwidth or something, or feedback loops with 1 gigahertz unity gain frequency. When you go to a the finer technology, in which all features are smaller, all parasitic capacitances are smaller, you can go to higher frequencies. Okay. Any questions on any of this? So, when we are designing a feedback loop, we would like to keep the second pole well beyond the unity gain frequency. Okay. Especially we are talking about feedback amplifiers, right. So, maybe the lowest we will make is the second pole being at 2 times the unity gain frequency, but we would like it to be beyond that, okay, because we don't want peaking in the frequency response. So, what's the effect of the additional pole P2? We saw that as far as the integrator's response is concerned, it's like delaying the response of the integrator. Okay, it delays the ramp by 1 over P2 seconds. Okay. So, the loop gain would have been an ideal integrator, but in this case it's an integrator with some extra delay, okay, which tends to cause instability. Now, does this system actually become unstable? So, if you strictly speaking, the instability is if the roots are on j omega axis or in the right half plane. So, that doesn't happen. That happens only in the limit of P2 being extremely small, right. But it does become, but for the purpose of designing an amplifier, having a lot of ringing is like instability. Even though it doesn't go out of bounds, that's not a response that you want. Okay, so so you don't want to have a condition like that. So it tends towards instability, but doesn't actually become unstable. But if you have an additional pole, let's say that is you have P2 and P3, then as you lower the value of the poles, the roots will move into the right half plane and it will actually become unstable where it will oscillate. Okay. So, critical damping happens when P2 is at 4 times the unity loop gain frequency. What I mean is 4 times the unity loop gain frequency when P2 was not there, right. And you have maximally flat magnitude response when P2 is 2 times omega u by k. Yeah, something, I mean, basically a lot of ringing in the time domain response. No, strictly speaking, instability means that there should be an output without an input, a sustained output without an input, which will happen only when the roots are on j omega axis or in the right half plane. But when I say tends towards instability, means that if you apply a step, it takes a long time to settle down. It will ring around the steady state value.
Do we specify any certain criteria to what extent we can use the instability criterion or just?
Yeah. So the one criterion is critical damping. Maybe you specify that should be no overshoot in the step response. Okay. When you apply a step, you know that if it is overdamped, it will go slowly, and as you move the poles closer together, it will move faster, but it will still not overshoot. So this is the fastest you can settle without overshooting. But if you try to increase the quality factor beyond this, it will do something like this. Okay. And depending on what your settling accuracy is, this may be acceptable. So what is an acceptable amount of ringing very much depends on the application. Okay. So maybe depending on the error value, a little bit of overshooting and coming down is acceptable. But certainly, I mean, when you make an amplifier, something like this would not be a good thing. Okay. So this could be an amplifier. It could be, I mean, not an explicit amplifier. It could be something like a voltage regulator. Okay. There also such thing like, I mean, things like this are important because a voltage regulator is supposed to hold the voltage despite changes in load currents and so on. So a change in load current is like a step response applied to some point. Okay. It's a step current that's applied to the output. Now, when you have a step current applied to the output, the voltage is supposed to be held constant. That is if it's an ideal voltage source. Now, in a real voltage source, what will happen is there will be a small amount of disturbance and the disturbance dies down. Now, if it rings a lot, that means that when you apply a step, the voltage will do something like this. Now, this is not the behavior you want from a supply voltage, right? You would like the output voltage to be constant. Is this okay? What I mean is, if you have a voltage regulator, maybe at some point of time you have a certain amount of circuitry switched on, and some other point of time you have some more circuits switched on. Now, when you switch on and off circuits, the output voltage of the regulator is not supposed to change at all. In reality, you know that won't happen. In fact, I have showed you that in this particular case, I have applied a step at some point. But if you apply a step at any point of this loop, you will see the same denominator and similar kind of response. Okay. So if you have a lot of ringing, that means that the voltage will change from the ideal value and will be changed for a long time. Okay. And also the amount of change can be a lot. So that's not the response you would like. Okay. So if you make a voltage regulator, the static specification will say the voltage has to be this value to this accuracy. Okay. Maybe 1.2 volts plus minus 5% or whatever the accuracy for that application is. And the dynamic specification will specify all kinds of things, like if the input voltage is changed in a certain amount of time, the output voltage should not, should settle within a certain time. And similarly, if the load current changes, then the output should settle in a certain amount of time, etc. Okay. So to meet all of those things, you will have to have the circuit critically damped, or maybe just allow a little bit of ringing, not too much of it. Okay. And sometimes you are concerned only with the steady state magnitude response. So in that case, the best bandwidth you get without peaking in the magnitude response is maximally flat magnitude. Okay. If you lower P2 beyond this, the bandwidth will reduce and also there will be peaking. So in absence of P2, what is the gain bandwidth product of the closed loop amplifier? The way we have applied the input? Omega u, right? So it is K times omega u by K. So this is the gain and this is the bandwidth. And when P2 is there, but very large, very high frequencies, what's the gain bandwidth product? Same thing, right? Because we saw here that this is the 3 dB bandwidth, which is still omega u by K. Okay. When P2 is at very high frequencies, the bandwidth is still omega u by k, and the closed loop gain is k. So, when P2 is much greater than this, again it is k times omega u by k, okay, which equals omega u. And what is the gain bandwidth in the maximally flat magnitude condition? Root 2 omega u, okay. When P2 equals 2 times omega u by k, this is, the gain is still k, the bandwidth is root 2 omega u by k. So, this is square root of 2 omega u. So, by adjusting it for the maximally flat magnitude condition, you actually get a larger gain times bandwidth product. So, that is a motivation to do that, okay. Now, this is what I meant by specification of high speed op amps. Now, an op amp is, as you know, op amp can be used with any feedback factor above a certain value, right. If you look at the specification of an op amp, it says that it can be used for unity gain feedback. That means that you can use it for any feedback factor, or it could be used for feedback factors less than half, and so on, okay. Now, if a high speed op amp at the highest value of or at the lowest value of k will be adjusted to give you this, okay. So, the gain times bandwidth will not be exactly constant. In fact, I would suggest that you look up some very high speed op amp, it will say something like, if you apply it in unity gain, the bandwidth will be 250 megahertz, okay. And if you make an amplifier of gain 10, what should be the bandwidth? If the gain bandwidth is constant, it should be 25 megahertz, but it may be something like 17 megahertz or something of the sort, okay. So, the gain times bandwidth is 170 megahertz, but when you apply it in unity gain, you have adjusted it so that the second pole P2 is 2 times omega u by k, okay. So, you can get a larger bandwidth than gain times bandwidth product by using the maximally flat magnitude response, okay. So, this is just so that you also understand the spec sheet of a commercially available op amp. If you look at any high speed op amp, this will typically be the case. At the highest, at the lowest value of gain, that is at the highest amount of feedback, you adjust it for q of 1 over square root of 2 or about that, okay. And you will also see from the data sheet that there will be some ringing in the time domain response. So, this gain times bandwidth being constant is true only for a first order system, okay. Now, when P2 is much more than omega u by k, it is approximately a first order system. What happens if you have multiple poles? How will you analyze it? So, let us say I end up with 3 poles, okay, and I quickly want to see whether it will be in the critically damped. I mean, I can't exactly define it, but I want some approximation. I want to be able to judge whether it will ring or not ring or what. Dominant pole. How do you use that? No, what do you do? Like, let's say I know that I have some P2, P3, P4, and from these values, without solving the 4th order equation, I want to, okay, how will I do that? Choose the smallest pole. Okay, that is one way. That is, if P3 and P4 are much more than P2, I can probably do that. But let's say that's not the case. They are somewhat comparable, okay. If it was very large, yeah, I would have done that. That's correct. So, yeah, one thing is you look at the values of the poles. If already like P3 and P4 are 10 times P2, maybe you can neglect that and assume that it's a second order system with only P2. Then make statements based on P2 that we already have done. Okay. So, but let's even say that I have 3 identical poles. Yeah. Yeah, somewhere in the middle is what I want to answer. I mean, something that is a calculation, right? I mean, not some wild statement, but a calculation, but not a full-fledged one involving a fourth order equation. What is the approximation that I can make? Let's take two poles. Okay. So I know that, see, in reality, you will have a large number of poles. And making statements on, I mean, like solving all that is quite out of question. In that case, you go and simulate it. But beforehand, I want to be able to know something. Okay. During the design process, before I finish the design and do full-fledged simulations. Yeah, well, actually I don't know, but there is something even simpler. How did we start off yesterday? By analyzing what was the first thing we did when we put the second pole? Exactly, we looked at what happens to the integrator, right? So, this is the response of the integrator, omega u by k, and then with one pole, in the long term, you get the same ramp, but with a delay of 1 by P2. Okay. Now, if you have two poles, it will give you 2 by P2 and so on. And if you have multiple poles, in general, you can think of it as a delay of these. Okay. You can, roughly speaking, think of it as each pole adding a delay of its own time constant, that is the reciprocal of the pole. Now I can represent all of this by an equivalent single pole. Okay. So I add up all the time constants corresponding to the poles, and I say that it's one pole with that time constant. Obviously this is in error. I mean, this is not the correct answer, but it gives me a reasonable idea of what is going on. Okay. So does it work? What is so if you look at, this should work. You can try it for some examples, but obviously all these things work only when the individual delays are small to begin with. Okay. If each of the poles was at such a low frequency that you would have got heavy ringing in the response just because of that pole, this whole thing is useless. So I am assuming that the delays from each of the poles is small, then you can add the delays up and represent the effect using a single pole whose delay is the same thing. Okay. In fact, if you expand it, I don't know if any of you tried it, so if you expand it in partial fractions and plot the ramp response, you will in fact see that in the long term, the ramp is delayed by 2 over P2. Okay. So many times this is done, like the time constants are added up, but the basis is something like this. Okay. So that's about the analysis of the feedback loop with non-idealities. We saw the effect of DC gain that causes inaccuracy. The effect of additional poles is that they delay the loop gain. Basically they delay the response around the loop. That's the bottom line. Because of that, it has a tendency to instability. That is, you can always have a case where you are overcorrecting on one side and then overcorrecting on the other side. That is when you have ringing. If the delay is not as large as that, you may not have ringing. But then you do the full analysis and you see that you can use this beneficially in some cases. For instance, we were able to extend the bandwidth by 40%. Okay. So that you can use sometimes while making an amplifier. But in general, having additional poles is not a good thing, and you should definitely keep them beyond the unity gain frequency. Okay. So the whole business of frequency compensation is about keeping the additional poles beyond the unity gain frequency. So from this we can roughly take away a guide that all the poles should be, let's say, 2 times or 3 times beyond the unity gain frequency. Okay. And when we have too many poles of comparable frequencies, we can first do a quick calculation by adding up the time constants corresponding to the poles and assuming that that delay came from a single pole. Okay. So the bottom line is, maybe I'll go to the next page. So the kind of loop gain I would want to see in a good amplifier, that is an amplifier which doesn't have peaking in the frequency response or ringing in time domain, will have is a 20 dB per decade roll off up to unity gain. So this is the magnitude of the loop gain. Okay. And I can have additional poles beyond this, or even parasitic zeros beyond this one. Okay. Now we also know that if the effect of poles is too much and you have facility to add a zero somewhere, you can do that to cancel the effect of the pole. Okay. Because each pole delays the ramp response, each left half plane zero advances the ramp response. So you can use that to some beneficial effect. Okay. But if you have only poles, this is the type of picture I would want to see. I want a first order roll off up to unity gain and a little bit beyond it, and all of the parasitic stuff should be happening there. Okay. Yeah. Pardon? Okay. Yeah.
Like the higher frequency components are more there. So how does that delay in the response and increasing the higher frequency component match?
So I don't know how to easily explain it. I mean, the easiest thing I can say is you calculate it and see, but you end up with complex conjugate pairs, right? So what happens is, so let's say this is the frequency response of an amplifier. Okay. Now, if you have complex conjugate poles at certain frequency, the system rings at that frequency, right? Okay. So firstly, what does this frequency response mean? This frequency response means that if you apply a sinusoid at this frequency, you will get this times that sinusoid and so on. Is it past time? Yeah. So now, if you have complex conjugate poles, the system itself, the natural response of the system is to ring at that frequency. Okay. So now what happens is, you see that the response is getting attenuated. So what I'll do is, I'll place some complex poles just beyond where it is starting to roll off. Then the system itself likes to ring at that frequency. So if I apply a signal, its natural response will help the force response also. Okay. Because without this, the tendency was to attenuate the sine wave. Okay. Now let's take a band pass filter for instance. Its transfer function will be something like this. Okay. So that means if whatever signal I apply, it tends to first ring at this frequency. Okay. So what I'll do is, I want to extend the bandwidth of this a little bit. So I'll make it ring a little bit at this frequency. Okay. So before it was attenuating, but its own tendency to ring will increase the amplitude at the output at that frequency. Okay. Roughly speaking, that's the explanation for why it enhances the response. Now clearly you can try to make it ring somewhere here, but what happens is it tends to ring only at one frequency, right? So then you may get some response like this or something like this. Okay. Now I don't want this emphasis in response at any frequency. I just want to extend the bandwidth a little bit. So I can't do it indefinitely, right? I can only do it just a little bit beyond what it was doing before. Okay. So when it was attenuating slightly, I try to make the system ring at that frequency. So maybe the natural, you can sort of think of it as the natural attenuation being compensated by its own tendency to ring at the frequency. Okay. So that's why in the sinusoidal steady state response, you will get a higher amplitude. Okay. Now if you try to overdo it, this is what happens. I mean, it will tend to ring a lot here, but the tendency, I mean, it doesn't tend to ring here. So you will not get a flat response.